dear chairs of the conference, dear distinguished guests, dear colleagues and friends, thank you very much for the invitation. I'm very happy being here, and I'll try to link from the geological model to the geotechnical design, how we can translate, how we can put numbers in geology, and how we can reduce any uncertainty related to that. So I'll start. I will follow the template I was given, so there is this slide, but I won't repeat this background of mine. I'll go directly to the outline of my presentation. So first I will give a short introduction, and then I will speak about the need for the quantification on the materials and how we put numbers in geology, and then how we use the geotechnical classification systems for geotechnical design to characterize and to estimate the rock mass properties. And then I'll try to go a little bit back and see where we may miss the road towards retaining the realistic, what we say, geological nature, and of course then geotechnical particularities that is hidden behind that. And I will highlight a lot the importance of ground behavior, not only putting a number and properties, but also assessing the behavior, and I will close with my remarks. So my introduction, why this theme? The charisma to be in the hybrid zone of an orthodox synergy between geology and mechanics, rather than any other types of geotechnical practice. You see in small letters on the top, my Greek origin, try to connect that. Why this theme? The magic of prognosis by the stochastic organization of all methods of the geology and the diagnosis of geotechnical problems. Why these themes? The plethora of tunnels under genesis in the whole cosmos for which technology is in anathema. So, just to put us in the wider geoengineering umbrella and family, we are a family in geoengineering compiled by engineering geology, rock mechanics, and soil mechanics. We call it geoengineering, and this comes pretty much very old, starting from ISSMGE, and then in the 60s, after two great disasters of big two dams in rock engineering, in Malpasset dam failure and Vayum dam failure, immediately the ISRM, the rock mechanics, and the engineering geology were born. So it was pretty clear in the late 60s, in the previous century, that what we are assuming as geoengineering is compiled by these three pylons. And the three basic areas of activity that encapsulate the practice of geotechnical engineering starts, of course, from the ground profile and understanding of geological genesis and evolution, and then predicting the ground behavior, and to the idealization process that the reality is ensured, that is modeled properly. So I'm using this Berland's triangle, the emeritus professor from Imperial College, in order to highlight that from a geotechnical engineer, one of our pioneers. And of course, the first section, the first question an engineering asks is numbers. So asked from a geology to compile a geological model and give properties, give some qualitative but mainly quantitative information. But what we actually have the basis of the subsequent geotechnical design is to provide the ground types, then the failure types, and then we go back and assess the design parameters. And of course, then we can proceed with the analysis and dimensioning. And now we have to go back and say that what we are asking from a geological model, actually what we ask is to reduce the uncertainties behind that. So it has to do with the composition, has to do with the structural disturbance, has to do with the spatial changes of the geological particularities, of course with the groundwater and the stress environment and anything related with geological hazards. So when we compile the geological model, what we want is to reduce this uncertainty. We want them to put it step by step in this geological model. If we don't have the time or the budget to assess a very detailed ground investigation program in order to have a very strong geological model, then we really need to have an appropriately adaptable design. So what we ask from the geological model, notice only what we are expecting, but also in 3D area to identify all these uncertainties. So it's a pretty big task. So let's go to the quantification of the geological materials. Now, we know that we have made tremendous steps in geotechnical design as far as powerful computer is concerned. We do very fast, very analytical design. So we really need to care about the inputs of that. So, and how we characterize all the geological materials behind that. Have we made the same similar steps in the geological characterization? Because we need numbers of strength or deformation for a tunnel, for a foundation or a slope. So late Dr. Everett Cook addressed to one of his, the most prestigious lecture of engineering geology world in Glossop Lecture in UK, saying that, look, we need to put numbers in geology. I understand that you are very delicate and very sensitive in order to characterize anything which is geology, that we cannot do that. But on the other hand, any physical identity can be described in mathematical terms. So we need to strike a balance between that. So it also said that the responsibility of an engineer is not just to compute accurately, but to judge soundly. So an engineering geology comes here. And what we have succeeded so far is through the ground investigation methods, of course, a remarkable extent and analysis on that. Also, we have made a lot of steps in geotechnical classification, but I will put a little, go back a little bit, step back after almost 30 years of experience. So what we are doing in rock mass characterizing, in rock mass types, we have a problem of laboratory tests in order to characterize, assess the properties of the rock mass through laboratory. You can understand that we can have only the intact rock measured. So this is not feasible many times. And in situ tests are very expensive, or again, we have a scale effect. Of course, back analysis is the best way to characterize a material, but you need to have a failure, you need to have a kind of deformation in order to back analyze, and you have your project running already. So we have the use of rock mass classification for this issue in all our engineering projects that are on or within a rock mass environment. So it is an empirical, it is direct, it is very friendly. So it is a vehicle to characterize and a common, let's say, language between geologists and engineers. So we have compiled, you can find in the literature dozen of rock mass classification, and here are listed some of the ones that you can identify, you know, and you are using them in your designs, many of them. And you see this is a map of different, for minings, for rock slopes, that we use the rock mass classification, but the issue here is not to compete them and say which is the best against the other. We need to go back and see what we are asking from this number. So we cannot hide, we cannot put all the information behind only one number in rock mass classification. So we need the geological model. If this is poor, everything projected on that is very, there's a big uncertainty behind that. And then we can say that after many, many decades of use of these rock mass classifications, we can really appreciate that they help us provide an invaluable help in constructing thousands of kilometers of tunnels. So we need to acknowledge that. And many times the rock mass classification, it is a connection and common language between different kind of disciplines in order to communicate with each other. And rock mass classifications, many times, is a decision-making number in order to select a support category, or even a TBM selection many times. And then, nowadays, we have the rock mass classification estimating the rock mass properties. So we have nowadays very powerful computers, analysis, 2D, 3Ds, but of course we have a huge advantage that it is the most accurate method. But of course this very accurate method depends a lot of the assumptions we have made and the numbers we have assumed on that. So calculating stresses, strains, and displacements really is dictated by this characterization. So let's go to the use and put in numbers and use them appropriately. So what we ask is to translate this scale to see now what we are excavating and the diameters that are affecting that disturbed rock mass after our excavation with a given method. So we really need to try not only to characterize, qualify, but also quantify. And then we have to go back to the rock mass type definition, of course. So we need to see from the geological history. So genesis is reflected on the quality of the rock, intact rock, and the inherent structures. Then we have the tectonism that reflects to the rock mass structure and the quality of the joints. And then we have the paleogeographic evolution reflecting on the structure and of the intact rock disturbance, but also on the rock mass disturbance. So Dr. Everett Hook and Professor Paul Marinos, they really saw that need. Not only respected the importance of the geological conditions, but they incorporated into the GSI, the Geological Strength Index. So they both have a strong belief that any design, any number must be accompanied with the geological identity of the material in order to understand also what is behind, what is below, what is next of that ground investigation assessment. And of course, they have compiled many, and together we have worked a lot in order to characterize different kind of geological environments. So nowadays, we need strong inputs. So we need to characterize, we need to put, to find the strength and deformation of the rock mass. So the GSI is such a classification used in the Hook and Brown failure criteria. So based on the structure of the material and based on discontinuities, then you can assess here, for example, a very blocky and heavily jointed rock mass by saying that in the core or in the outcrop or in the tunnel face, then you can characterize, and what you can see, you can really put it in the, projected on the chart. So you're not lost just in numbers, but you also visualize your material. And here is another example of a fractured limestone in a fault zone. So then once you quantify with the GSI, then you can put in the Hook and Brown failure criteria, the intact rock parameters together with the GSI and the disturbance factor, and then actually with this transition equations, you can penalize your intact rock and find now the properties of your rock mass. So once the GSI has been selected, then your system becomes highly quantitative, and this can be an input for numerical analysis or closed form solutions. And now I have to say that this is not in comparison with the RMR or Q, which were born in order to identify, in order to guide us for temporary support philosophy. Is just function to estimate the rock mass properties. So the intact rock on the one side properties and the factor is using the strength of the intact rock with the GSI and disturbance factor is the numerical ID for isotropic rock mass for analysis. So if you combine, you see different colors in your left chart. So these colors are different rock types. So you see the ranges of the intact rock properties. So we need to give a lot of attention to the intact rock properties in order then to reduce it through a GSI. And on the right side, you see different bubbles, means different ground types based on this tectonism, weathering and alteration, which we're gonna see. So this is something to show that we really have a dispersion, combinations depending on intact rock properties, but also the geological history through the rock mass characterization. So, for example, here in the projects of the Metro of Athens, you see a lot of lines. We have many challenges here relating with very weak rock masses, the TBM selection, and technical and contractual assistance. So we have two units. We call it an Athens schist, which is the main rock formation. And you see there are a lot of different kind of materials depending of some of them with brittle nature, meta-sandstone, and some of them more ductile, meta-siltstones or clay shales. But mainly we have a lot of thrusts. So you see something which is very complicated here. And here are some boreholes that you can have an idea from the upper Athens schist, which is better than the lower part because it's due to tectonism and due to the origin of the rock masses. So you see in the upper Athens schist we can range qualities from blocky to very blocky to brecciated in the same material. And this section I showed you in 2 slides before is just a fraction of a line. And you see from a borehole to another one, we can have this differentiation. This is not just a fault zone. This is the whole nature of the material changing from meter to meter. And then you go to a material which is more ductile, so it can be more sheared. It has a weaker nature by itself, by its origin, because it's a shale, a black shale. So you have more laminated, very folded rock masses. And when you core them, you understand this is very, very difficult to identify where is a soil-like or a rock-like and how we characterize this in terms of rock mechanics. So it's a pretty challenging work to do. So here the GSI comes and quantified in this heterogeneous nature of rocks per meter, and then you have these bubble charts per core run, and you see where, for this specific part of my tunnel, we have these different kind of rock mass types that we can assume that we can find. On the same time, we have the laboratory test per lithotype, per meta-sandstone, meta-siltstone, clay shales, sometimes some calcitic meta-sandstones. So we have a combination of intact rock strength, GSI range of values. So we have a set of parameters to assess. So this initial geological model that the engineers doesn't feel very comfortable into proceeding to geotechnical engineering can be transmitted to this geotechnical section by putting a set of GSI, sigma CI, MI, so intact rock with the GSI, and then we know what to encounter and how we can proceed with our analysis. So we need a really roadmap. When we use these rock mass classifications, since they are empirical, we need to find a way not only to help us assessing the properties, but also to help us not losing any other kind of geological hazard that we can have in our project. So let's go using this GSI incorporating the geological uncertainty, which was our primary also goal with the geological model, not only putting numbers. So how tectonism, how weathering, how alteration. I'm using these processes, which are pretty common to all the areas, because they produce in different rock mass types, but also they are hiding threats behind them, geological hazards. So how tectonism, so from low to moderate to severe, something which is brittle kind of nature, we know how it shifts in space. Something that is more ductile of nature, weaker nature, I mean in its origin, then we can shift also not only to the bottom due to the tectonic disturbance, but also to the right. So we can have poorer rock mass properties due to this lamination, due to this foliation of the rock mass. So you see this differentiation. And for example, in heterogeneous, tectonically heterogeneous rock masses, like flysch rock types, we see that we can have not only heterogeneity due to the nature itself, but also due to the tectonic disturbance. So in a specific fraction of a tunnel, we can identify from the geological model what kind of rock mass types we can have. So GSI can help us identify also the rock mass types, not only following numbers +1, +2, +3 criteria in order to identify one number, but also give us a map of what we may missing or what we can encounter, what we are searching for in our geological model. So you see here 11 rock mass types in heterogeneous environment due to tectonism. At the same time, here you see different kind of rock mass types in limestone rock mass. So you see different rock mass types that can have, of course, alternations with other weaker, softer material, but not so tectonically disturbed, which is, we are very happy about it, but then it becomes more fractured or more folded, with or without intercalations, or very fractured, or with high infillings. So how weathering reflects, again, we can see if we have a severe weathering or a slight or moderate, we can have shifting only in the rock mass structure or also in the rock joints. So we follow this, and you see very highly, this is for Porto from Portugal, very highly weathered. This rock, very highly weathered rock, can be below this left side of better quality rock mass due to these geological particularities. So again, this visual chart helps you identify and not losing. On the other hand, the alteration, which is another process, and it has to do with a bottom from below the surface to the top, this alteration of the fabric of the rock mass structure due to the hydrothermal or to automorphism. For example, here, ophiolites, you see how the rock can be transformed into a more clay-like zones or highly serpentinized rock that dramatically loses the intact rock properties. So you see again from none to moderate or from none to severe what you can encounter. In our tunnel, we can find in depths of 500, this is not due to meteorism, but due to other geological properties. And nowadays, of course, we're using AI in order to reduce and have faster properties. And we're working on that. We are research in order to characterize many cores from AI and identify in the best way our GSIs. So I have 4 minutes left, and now I would like to link with the rock mass classification with the behavior. So we have put numbers, we have characterized our rocks, but if we don't consider how the rock mass will behave before proceeding to any kind of analysis, then we may lose a lot of information and a lot of analysis. So in first case, we can have these very happy moments in the upper unit that I showed you, but on the same time, the same TBM can produce these very, very bad circumstances if you cross a different kind of behavior. So if we use a GSI, and we see that we can have different kind of rock mass types with the same GSIs. You can see a laminated rock mass, a disintegrated rock mass, and very blocky. You see that they're in the same diagonal, but they have a completely different behavior, from structurally controlled sometimes to shear behaviors or raveling ground. So we shouldn't just follow these numbers for our design. We need first to assume how the ground will behave. So we shouldn't use this rock mass classification as a cookbook. So you see in this example, a fractured rock mass with poor discontinuity surface and a brecciated with good discontinuity in the same in situ stress environment, in the same rock. So the same GSIs will give you equal stress conditions, you have equal rock mass strength and same shear stress problems around your tunnel. If you follow the RMR, you fall in the same tunnel support category. So again, you will assign the same support measures. So yes, they help us now characterize this rock mass and help us identify after excavation how we can communicate to the designer, to the owner, to the contractor, how is our rock. But putting that in every kind of analysis, we need to think about the behavior. So in one case, we have structurally controlled wedge failure. On the other hand, we have raveling ground or flowing ground. So the support philosophy is completely different. On the one hand, have to retain, keep the confinement, and of course, implementation of friction bolts in one case. On the other hand, you need to pre-support with some spiling or with your tunnel excavation step. So before following blindly any rock mass classification, we need to assess this rock mass behavior. So from brittle failure to structurally controlled or squeezing, we can have numerous of rock mass behavior types, and you can assess this from the structure of the rock mass. So you need to see the structure of your rock in the scale of your project, which is something that needs experience, and with the small or large overburden, and of course your intact rock strength. And then this behavior can give you what kind of analysis you proceed. Structurally controlled, or an isotropical or discrete element analysis, or squeezing kind isotropic one. So in this GIR, in this tunnel with the TBM, you see the material, which is heterogeneous. You have the rock mass type definition. We have all the numbers behind that. But before following any kind of analysis, you need to set behavior type 1, 2, 3, and 4, and link them with the ground type and with the given excavation method. So you can assess the squeezing potential, follow the diagram of the rock mass strength to the in situ stress ratio, and along your chainheads, using again the rock mass strength, and then along your tunnel, you can assess your rock mass behavior modes. I just need 1 more minute to close, because my time is off, and then you can proceed definitely to your numerical analysis. So you follow exactly the same path, but before using blindly the rock mass classifications, you also know how your rock mass type in a given stress environment, in a given hydrogeological regime, how will behave. So, of course, geological uncertainty is inevitably inevitable and can never be completely eliminated. Our work is to identify, evaluate with the advances of ground investigation, new technologies in order to constrain these uncertainties. Together with the rock mechanics and engineering geology, we can work together to assess this uncertainty and characterize the rock, find the rock mass properties and behavior. And we need to understand that this synergy is not just used behind one number. It's not only one number. They constitute an integrated interpretive science, combining observations, combining geological understanding, engineering judgment, and expected ground behavior. So rock mass classification systems should not be regarded as design recipes. Mainly, they are really practical supporting and interim solutions. They're really valuable to our tunnel practices. So we need to use them accordingly. GSI is a framework, it's a strong framework, not only putting numbers, but also using these charts to identify the geological nature and reducing this geological hazard. Predicting the behavior remains a primary basis for design, construction, and validation of engineering assumptions. With that, I would like, as a president of the IAEG and member of the FedEx, and we have the vice president of ISMGs here, so this Federation of Societies, we are preparing a big mega conference in 2030. We don't know yet who is going to get it. So I know that we have already a lot of national groups bidding for that, and we are very happy for that. So keep tracking this. And of course, our World Congress is in TU Delft next November. I also invite you there in our World Congress. And with that, I would like to warmly thank you for your attention.